So now let's talk about subnets. This is a short one. Basically, each subnet is a subset of the bridge domain. And we see kind of the hierarchy here from uni to tenant to the bridge domain. Now you might say, wait a minute, over here on the right, it looks like uni, then the tenant, then the VRF, then the bridge domain. And that's true in one sense, but it's not actually the exact hierarchy. So if we actually take a look at our model of our web user interface, we see that tenant has a subsection of networking, but that's not actually a managed object, that's just a folder or container. And then we see bridge domains are kind of at the same equal level to private networks or VRFs. So from a hierarchical standpoint, we have the universe, we have a particular tenant, and then equal or at the same hierarchy level, we have VRF, which is private network, and bridge domain. Now they have a relationship with one another. A bridge domain cannot exist without a relationship to a private network. So from a NXOS standpoint, it does have to be a subset of a private network. But from a management information model, it is not a subset. It's not a child to the parent of a VRF or private network. It is parallel, but it does have to have that relationship. Okay? The management information model is literally everything in ACI. So, and there are over 4,000 managed objects. Don't fret. We'll go over many of them as we unpack this more and more, and as this content grows, and possibly even as we go into probably an advanced course to this beginner ACI course. So we won't overwhelm you right now with all 4,000 managed objects, but managed objects and the management information model is really the foundation of everything in ACI, which gives it that ability for everything to have a RESTful API in a true REST sense, where we have full enumeration of parent-child hierarchy from that URL standpoint. So we do have the subnet. Whenever we define a subnet, they do have to have a unique IP within a VRF. We already mentioned that. Bridge domains can have more than one subnet. And subnets can span multiple endpoint groups. So subnets automatically create the SVIs where endpoints appear. We already talked about this. So taking a look at the web user interface, we have our tenant, networking, our bridge domain, and then as a subset of the bridge domain, we have subnets. So here we see multiple subnets, 192.168.10 and .11, and they're each .1. So we always create the IP address not of the network, but just of the actual SVI that we want created. And we use slash notation to go ahead and fill out the mask, or you can do it the old-fashioned way and not put the slash, fill out the mask, and it will automatically fill in the slash. So maybe you remember 255, 255, 255.248, and you can't remember what slash that is. It will fill it in for you. So then we have something that's confusing to most networking people when they first look at this, which is scope. So what is this scope? What's a public subnet or a private subnet? We're going to talk a lot more about this in a future module for external layer 3 routed, but this basically means if we have external routing turned on, and we most likely will, do we want this SVI to be advertised into the routing protocol? So for instance, if this were OSPF in an NXOS switch, ticking the box for public would be the equivalent of going ahead and saying IP router OSPF, process ID 1, area 0.0.0.0 or .1 or whatever area we had chosen. The nice thing about ticking the box for public versus having to say, and you might just say, well, why didn't they just say, do I want OSPF turned on? Well, basically, if we had more than one routing protocol, maybe we have OSPF, eBGP, and EIGRP. I don't know, we're going crazy. We have all of them turned on for routing outside of our fabric from this particular tenant. If I had those turned on for this particular tenant, and I tick the box for public, this subnet gets advertised out all three. Okay? So if I don't tick the box for public, it has to be private. Now these look like checkboxes, which in HTML or web typically indicates multiple selection. And this is kind of confusing because there is a subset of these three, and I haven't talked about shared yet, that is multiple selection or Boolean AND. But then there's also a subsection of these three that is Boolean OR. Okay, so that really should almost be radio buttons. So public and private, those should be radio buttons. And if you tick public, it should untick private. And if you tick private, it should untick public. But unfortunately, that's not the way the web interface was built. So if you tick public and private, and then you click save, you'll get an error saying a subnet cannot both be advertised and not advertised. Okay? However, so let me back up. For public and private, it can only be public or private. However, it can be public and shared or private and shared. So shared, what is that? This is VRF route leaking. So when I share a subnet, this means that this subnet is flagged to be allowed to be route leaked. But the question is, where is it being route leaked from what VRF to what VRF? Well, we already know from what VRF because this subnet is a subset of our VXLAN bridge domain. So it's inside of our bridge domain. And our bridge domain must be linked or associated to a private network, or VRF. So we know where it's being route leaked from. But the question is, where are we route leaking it to? This becomes a function of where do I have contracts from an EPG inside this bridge domain to another EPG in another bridge domain which is a part of another VRF. Now if I have contracts between two EPGs in the same bridge domain or between two bridge domains in the same VRF, the shared flag is simply ignored. But if I have a contract, if I have an EPG A inside bridge domain A, inside private network A, and the subnet is flagged as shared, and then within the same tenant, I have another contract for B. In fact, you know what? Let's just draw this. So I have within tenant, let's say 1. Okay, I have private network or VRF A, and we're just going to use A for all of this, and I have bridge domain A, and I have EPG or endpoint group for A. And within bridge domain A, I have a subnet, and that subnet is flagged as shared. Then I have private network B and bridge domain B, and I have EPG or endpoint group B, and I have a subnet, and again it is flagged as shared. So now, let's change my color here a little bit. Now I go ahead and create a contract from one side to the other, and it's provided on one side and it's consumed on another side. So at this point, because of the shared flag that we see here, if I have this flag shared from this subnet and then also from the subnet on the other side, so maybe this was the subnet on bridge domain A, and I also have the subnet shared over on bridge domain B, at this point we have VRF route leaking that is occurring. And we would have bidirectional VRF route leaking. This does depend on the contract, the way it's written. If the contract is a bidirectional contract, or if it's not, if it's just a unidirectional, then we would need another contract that's provided and consumed from this direction. Again, it just depends on how you create your contracts, but this is how the VRF route leaking occurs within the same tenant. There is an additional step that you need to do between tenants, and we'll go over that. But keep in mind, for now, this is, and let me just go ahead and clear off my board here for the next time I need it. This is essentially what you would, you know what, actually let me go ahead, and what I'm going to do is I'll save these as I go along. So I'll save them after the recording, and for right now I'll just go ahead and create a new layer and turn that off so that we can use it for the next one. And I'll save these and I'll add these whiteboards, and I'll try to be as precise as possible, but I'll add these as accompanying files to the class on demand. So you should be able to see it in your files here. So now we're going to go ahead and move back to actually before we go on to endpoint group, let's just make one note that on a particular subnet we do have the ability to include a route profile. And this actually allows us to go ahead and state what kind of tagging or features we would want to do from a routing protocol perspective. So really this would only make sense if this were a public subnet. And then if it were a public subnet, we would choose what is our layer 3 out. So maybe we're only linking it. And you might say, you know what? Because when I said earlier, if it's a public subnet, it's going to be advertised on all 3. Well, that's sort of true, but at the same point, we don't necessarily have to have it that way. Because if you recall back, and I'm going to kind of skip back a little bit to bridge domain, for a given bridge domain, which is where the subnet is a subcomponent of, we have to state what associated L3 out we are associated to or linked to. So if I had OSPF set up in a particular tenant on one external routed network, which you can see here, I'm moving my mouse below, okay? I had that, and that's what's called an L3 out, is this external routed network. So let's say I set up one L3 out for the protocol of OSPF, and I just called it OSPF. Then I set up a second L3 out for BGP, let's say eBGP, and I tagged it eBGP, okay? So I have 2 separate L3 outs. Just because I've flagged a subnet as public does not necessarily mean that it gets advertised out both eBGP and OSPF. It would only get advertised out where I had the bridge domain associated to a particular L3 out. So if I associated the bridge domain to both OSPF and eBGP, then it would be advertised to both. If I only associated it to eBGP or only to OSPF, it would only be associated to each one of those. To either one of those, I guess I should maybe say. So we'll go back to where we were at in subnets. And we also, so that's when we can, for the particular L3 out, use a route profile to do various, let's say, tagging or other features that we want to maybe set a BGP extended community or something like that. We also have subnet control. This is basically, I can use this particular IP address on a VXLAN bridge domain as my IGMP querier. Okay? So I can flag this as my querier. This would be the equivalent in traditional NXOS as stating in global config mode VLAN configuration, which is separate from just like your regular VLAN database, but VLAN configuration, the number of the VLAN, and then IP IGMP snooping querier, and then the IP address. So now let's talk about endpoint groups. Endpoint groups, or EPGs, are logical entities containing a collection of endpoints that desire the same common policy requirements. So for instance, the same ACLs or ports between them, the same QoS, or the same layer 4 through layer 7 services instantiated between 2 EPGs. Now, not necessarily everything inside of one EPG has to have the same contract to everyone, or the same security policy, the same ACL, the same QoS, or the same firewall or load balancer instantiated. That's why we can have a group of endpoints within an EPG and then have different contracts, which contracts are what enforce either the security or the QoS, or the L4 through 7, or all of them at once. But it's a relationship between one EPG and another EPG. So I could have an EPG for web, and we'll actually take a look at the end of this. We'll kind of put it together in a much larger context or bigger picture, kind of a 40,000 foot view, maybe not a 60,000 foot view, but a 40,000 foot view. And we'll talk about how, for instance, one EPG for web could have a contract out to public that allows them to only advertise port 80 and require firewall and load balancer. Another contract to common to consume resources such as Active Directory and DNS. And another contract to my developers that doesn't require any firewall but allows them into maybe an ACL, no stateful firewall, no load balancer that allows them into port 22 for SSH, something like that. So the endpoints are entities that are either directly or indirectly connected to the fabric. These could be physical bare metal machines. They could be VMs attached to a hypervisor. They could be L2 switch or L3 routers. So these devices are going to have an address, which is their identity. Could be a MAC address and an IP address, or only a MAC address. But we're on Ethernet, so it does at least have to have a MAC address. The location is going to be identified by where they show up, and it will be mapped to that VXLAN VTEP for the leaf. And it could have multiple attributes. We'll actually talk about how with VMs we can match up to 10 attributes coming from ESXi. Simple things like IP address and MAC address, more complex things like the VM name. And we actually have something that's very new in ACI that I don't actually have slides for in this module, but we will talk about in a specific module all of its own called micro EPGs, or sometimes referred to as microsegmentation. So within one major EPG, and first of all, we really have to talk about the VMM, or Virtual Machine Manager. But once we talk about that module, we'll circle back and take a look at EPGs, microsegmentation within Virtual Machine Manager domains, micro EPGs, kind of the same thing, not really kind of, but the same thing, different name, and how we can create those micro EPGs dynamically on demand with no administrative intervention other than the initial setup of which attributes do we want to match based on attributes, up to 10 attributes that come from the VM, including, for instance, VMware uses something called custom attributes. We can even match on that. So really, it can match literally anything you want it to be. So for EPG policy enforcement and mapping, the policy is set and the security enforcement occurs at the EPG level based on really in the leaf switch for each EPG. So communication is allowed between all endpoints within any given EPG, but remember how I talked about the fact that we're going to be able to, in a future module, take a look at micro EPGs, which would allow segmentation between devices if they are Virtual Machine Manager managed, right? So if we're, for instance, if we're in VMware vSphere and we have vCenter integration, the VMs that appear in our ESXi hosts do have the ability to be dynamically classified based on a couple things that we set initially into their own micro EPGs within a macro or overarching EPG, and communication between those would be blocked. But otherwise, unless we set up those micro EPGs, then we do have the fact that within any EPG, communication is allowed. And now I remember communication between EPGs is not allowed, but within, unless we're setting up micro EPGs, it is allowed. So the network constructs are completely independent of the application or the EPG. So for instance, I might have web servers, maybe Apache servers with OpenSSL that is running within EPG web, and some of them are on the 10.10.11 subnet, and some of them are on the 10.10.10 subnet. Okay? they would have communication. They would be able to route between them because I'd have a single SVI with a primary IP and a secondary IP. So they would be able to route between them. And unless they were in micro EPGs, which here they're not pictured, they would have communication between them. However, they certainly could have two separate ranges of IPs, 3, 10, 20 if we want, without the concern of ARP or unknown unicast causing too much of a problem, because we have the ability to turn those broadcasts into unicasts and only send them directly to where they need to go. So endpoint groups, we have the ability to classify based on VLAN, okay, or a physical port, or a VXLAN, or even an IP address subnet. Now this says future, but truthfully, we have the ability to do this today. So we already have support for Microsoft Hyper-V now with the new release of ACI. We can take a look at custom VM attributes. So going back to how do we classify a particular device that connects into our fabric, into a leaf switch, into an EPG, this is where let's just go over this. The endpoint would attach to the fabric. So if this were a physical machine, maybe it boots up, or maybe someone plugs the network cable in. If this were a virtual machine, someone powers on the VM, or they move it to a particular, they do a vMotion, and all of a sudden it's seen on a new leaf switch. So at this point, the APIC detects the endpoint, and it learns about its source EPG. Now, how does it do this? Based on these different attributes. So let's say the VM is coming from let's say an ESXi server that's a part of a distributed virtual switch, and of course it has a port group. The port group has a VLAN ID that's tagged, or it could even be a VXLAN ID if we were using, let's say, vShield. And we could go ahead and sense or see that .1Q header, see the VLAN ID, or see the VXLAN header. And from there, we would have specifically set already in the EPG, we would have said, look for this particular, actually, let's say it was a VM, okay? Remember, and we'll talk a lot more about this in detail in the module dedicated to it, but remember I mentioned briefly, I think in the last module, that when an EPG gets created and attached to a VM domain or a vCenter, it creates dynamically a port group in the vCenter on the distributed virtual switch with the VLAN ID that it pulled dynamically from that VLAN pool with dynamic allocation. So because of this, this is what would allow ACI already has that mapping because it actually did the assignment for the port group and the VLAN ID. So it sees the .1Q header come in. It says, oh, I know that .1Q header, and I know that that port, either the leaf switch has a VLAN that's unique, or remember from the last module we have PPV or per port VLAN. It could just be that from that port it's unique. And I see that that port is attached to an AEP, which is an attachable entity profile. That's associated to the domain, which is the VMM domain. That's associated to the VLAN pool, whereby the allocation was already provisioned for that VLAN ID to create the port group. So I already know the mapping. I see the VLAN ID, that is the leaf switch speaking, and I see the VLAN ID. I know to go ahead and classify that VM in this EPG, because the EPG is the creation of the EPG is actually what pulled the VLAN and sent it to vCenter. Okay, so APIC based on the leaf switch, or really the leaf switch possibly itself, and we'll talk about what the difference would be here in just a moment when we go down here. So don't read ahead, it'll just confuse you. It derives the source EPG, and then the APIC pushes the required policy to the leaf switch. Now I thought we said that the APIC is not in the control plane. Okay? Remember, it is declarative. It's not telling the switch exactly what to do, program port XXX. It's declaring the intention of the state, and it's actually up to the switch to implement that policy or state desired. Now, it depends at this point on the actual immediacy that we have provisioned, so we'll get into this stuff, as to whether the APIC needs to be involved or not. So first of all, let's talk about the policy being pushed to the leaf and then programmed in the leaf node hardware. So first of all, when we say policy push to leaf, actually let's just say that we're going to set both of these, kind of do a higher level, and then we'll drill down. Let's say that we set both of these to immediate. At this point, the APIC is, as soon as we actually see a hypervisor physical NIC attached, and we either recognize via link layer discovery protocol or also CDP, even though it's not written here, or we'll talk later about OpFlex with AVS. As soon as it sees that hypervisor, the policy would be pushed down from the APIC into the leaf switch, even if the VM had not yet been seen. Okay? And when we say it's pushed down, we really mean into the hard drive, into the Linux OS, into the managed object configuration files. And then in terms of being policy programmed into the hardware, we're really talking about, right, TCAM space for ACLs or stateful firewall or things like that. That would be this instrumentation. So the first is resolution. Is the policy pushed down to the SSD hard drive that's running there, into the Linux OS, into a managed object configuration file? The second is instrumentation. Is traffic even actually being programmed into the ASIC? Okay, possibly into a TCAM. Okay, at this point, the immediate would go ahead and push everything down, whether or not we actually had a VM show up or not. So in this state, or in this case, the APIC does not have to be alive on the network at all. All three APICs could be dead and gone. Of course, we'd never make any changes after that. But all three APICs could be removed and thrown in the trash, and the fabric will absolutely continue to work flawlessly. Okay? The problem would become if we wanted to make changes, of course. However, if we set these things to on demand, then let's just review these one by one. If we set the resolution immediacy to on demand, then the policy would only be pushed to the leaf node, to the managed object, Linux file system, configuration files, when a physical NIC was attached from the hypervisor and the VNIC was associated with the port group. Note that we don't need to see any data plane traffic yet, okay? But we do need to see, we need to learn from vCenter that the VM has been associated to a particular port group. Then, when it would be pushed to instrumentation, or the ALE ASIC, this would be on demand, or if we set it to on demand, it would be programmed into the CAM table when reachability was learnt through the data path. So this is actually when we see traffic from the virtual machine. Now, what I see happen a lot is policy for resolution immediacy is immediate, but then instrumentation immediacy is on demand. So this allows me to keep my ASIC, my TCAM space free, but and TCAM I haven't defined that, but you should probably know TCAM or CAM. TCAM is ternary content addressable memory, right? So ternary 3, okay? So we have, we care about the bit, we don't care about the bit, or XOR, we don't care whether the bit is set, you know? We care about the bit, it either needs to be on or it needs to be off. We don't care about the bit, or we, you know, actually it's on, it's off, or we just don't care whether it's on or off, okay? So that's ternary content addressable memory. Extremely fast memory, far, far faster than you know, NAND or flash, or you know, I can't keep up with the latest SODIMM, you know, whether it's DDR3, LLDR, anyway. I forgot what exactly. It's way faster than that. So it's very expensive, and so we have very limited amounts of it. So at this point, we have an idea of how we classify traffic. And then also one other thing to note, if I actually go back a little bit, there it is. At the bridge domain, we actually saw this unknown unicast traffic class ID. This class ID is I didn't kind of talk about it then. We'll talk about it real briefly now, and we'll take a lot more of a look at it in some of the demos. So this class ID is really what's used for security. And note in the bridge domain, we only see unknown unicast traffic get this class ID. But I should go ahead and note, as I flip through these slides, that for endpoint groups, we actually do have, specifically, we do have a class ID per EPG. Okay? So this is actually how, when we take a look in the next module about the VXLAN header, and we talk about that we have space in the header for the EPG, we're not placing the name in the VXLAN header, but rather each EPG has a class ID, and that's essentially what goes in the VXLAN header to identify a particular VXLAN packet, not only as belonging to a particular VNI, which is also in the VXLAN header as a separate field, okay, so which layer 2 bridge domain, but we also have carried in the VXLAN header, and so able to be switched, routed, firewalled, and everything else at wire speed, at line rate, for all size packets, depending on the leaf switch, of course, is the class ID. And really this equals the EPG. So this is how security is done. If we take a look at our contracts in detail in the leaf switch, our zoning or our firewall, our ACLs, stateful or stateless, those are all done matched by source and destination EPG, or really source and destination class ID.